Okay, our next presenter is Dr. Kingsley Obodo. Okay. He's going to tell us a little bit more about computational modeling using HPC for material prediction and design. Thank you, Kingsley.
Thank you very much. I'd like to thank the CHPC for this opportunity to give a short presentation on the work I've been doing recently in computational modeling. Just want to try and figure out the pointer. All right. So currently based at HISA, so I'll talk about it in the next slide. This work was done by me and a couple of other people. So I just included Cecil Oma and Dimitri, which is my boss. So the next slide, please. So in this presentation, first of all, I'll just tell you a short story about myself. Then I'll give you an overview of what I would like to talk about. So the presentation is sort of divided into two aspects, looking at 2D materials and catalysis. So the next slide, please. I'm from a tiny village here, somewhere around here. I don't think a lot of you have been to Nigeria, so it's very good to kind of have a perspective of this picture. The reason is because Nigeria is pretty green, like Durban, where I'm from, is pretty green. So I'm from a state called Enugu. So my local government is Amandi Molo, Isiagu. So I'm an Igbo guy. I think that's how we say it. So yeah. So next slide, please. So currently, you can just think about the distance from here to there. That's about 6,500 kilometers. So it's kind of really far. And I'm in a small town called Potchefstroom. The great thing about Potchefstroom is HISA is located there. So as well as Professor Connie here and a lot of people here. So we've got a very beautiful university. So you're all welcome to come down there. And one thing about the university is that we're like very focused on research as well as teaching. So I'm more in the research part of the university. So HISA was formed out of the need to beneficiate platinum and develop new hydrogen resources. Not just compressed hydrogen resources, but we would look at different forms of hydrogen resources. So LOHC, which is liquid organic hydrogen carriers, which will be some part of my talk, water electrolysis, which is some part of my talk as well as building infrastructures that would form part of the mainstream energy corridor for South Africa. So talking about, we all quite aware, so I'm not going to preach to this audience about the need for new and diversified energy forms. So next slide, please. So in my previous slide, I sort of motivated why we need to think about energy and the need for thinking about energy in innovative ways. And so one of those innovative ways is doing computational experiment, computational design, and computational modeling. So this crowd is kind of the right crowd, so I don't need to say anything about that. And the key questions, like I mentioned before, that I want to answer is photocatalysis and photovoltaic systems and 2D materials, liquid organic hydrogen carriers, as well as water electrolysis. So these are the three fundamental questions that my talk is kind of based on. And this talks to the other part of this talks to the concept of energy storage, development of new advanced materials, and fundamental understanding of processes involved in renewable energies. Next slide, please. So 2D materials is something that is quite common and quite known. So I just showed this slide just for you to kind of have an idea of what we do. So the systems I studied here are quite kind of really small. So you have about 10 atoms. So this is just looking at 2 bilayers. So the problem here is that why HPC was needed was, if you look at the kind of calculation I was doing 12 times n, where n is about 4. So this is about 120 calculations. So if you think about 120 calculations, on my small computer is doable, but then it's going to take me about 6 or 7 months. So it's not very practical. And then I need to introduce hybrid functional, so it makes the calculation more computationally intensive. So this is why HPC was needed in this study. Next slide, please. So this work has recently been published. So I just showed some of the configurations we considered. So if you look at the configurations, we consider different stacking patterns. So if you look at the table on my right, you will see that just to determine the binding energies, we considered so many configurations. And This just calls for the need for HPC. So from here, we kind of evaluated and we found the lowest energy configurations, and those are the lowest energy configurations for these genus transition metals. So I want to say something that the genus transition metal that chalcogenide just borrows from the concept of genus, which is like the Greek mythology of having two phases. So you kind of have your transition metal in between. So you have a different chalcogenide on the top and on the bottom. So we use the concept of that to sort of engineer the band gap. So, and then to form new and novel heterostructures. And so we found the lowest binding, the lowest structures, and we use these configurations in our further evaluation. Next slide. So I decided not to show everything, but just to highlight some of the key results. So if you look at the table, on the table here, I have shown the valence band and the conduction band maximum and the band gap calculated using both PB and HSC. So why it's important is that we know that the classical PBE tend to underestimate the band gap, and it's not good for certain kind of stuff, for certain kind of reactions. So we have the ref PBE, the RPBE. So, but using the hybrid functional, these can give better description of the electronic band structure. So the plot you have here, figure A, is just showing it's just showing the plot. Figure A, we're showing the water splitting reaction. So in this reaction, you need to align the oxygen evolution part and the hydrogen reduction and the hydrogen evolution and the oxygen evolution part of the reaction. So this will tell us if, sorry that this pointer doesn't work, but no, just next slide. Yeah. If this line falls just about outside there, and if this is outside there and something like that, it will tell you that this is a good material for both oxygen evolution and hydrogen evolution. So it will photocatalytically split water. But in this case, you see that this just falls in between here. It tells you that for the hydrogen evolution part of the reaction, this material considered is not good, but for the oxygen evolution part of the reaction, it's good. Here, we just showed how our band gap straddles. And so we have a type 2 band gap. So the good thing about type 2 band gap is that you don't have recombination reaction going on. So the recombination is when your host and your exciton kind of mix. So this will kind of make the device not favorable for photocatalytic application, which we evaluated. The good thing we found here is, like I mentioned, that the catalysts we studied are good for one part of the reaction, oxygen evolution, but not good for the other part. That's something good, but it's not that great. So further investigation that we intend to do is to look at band engineering by straining. So for the photovoltaic aspect, we found out that we kind of have reasonable, not the greatest photovoltaic material for this genus material. So in principle, we've created this material, but we found out that it's good for something, it's not good for something. We went further to look at another genus transition method, the chalcogenide. So next slide, please. So in this work, you would find out it's sort of an improvement of what we did before. So we considered the genus transition method that chalcogenides with WSE2, which is also a transition method that chalcogenide. The good thing about this was all our configurations we considered, they form stable they have stable binding energies. It means that the stacking of these systems would form. And we took the lowest energy configurations. Next slide, please. So the PEC we calculated here, they are significantly high. So this is to determine what is good for photovoltaic systems. So they are reasonably high, and they are higher than what has been reported for several systems. Now, the second thing is that we found a good configuration, WSETE and WSE2 heterostructure, that is good for full water splitting under both the basic and acidic conditions. So now it's something that I'm not sure I have experimental colleagues here, but it's something that would be nice to synthesize experimentally. So this is just similar to what I explained in the previous slide, where we looked at the energy versus the vacuum layer of our system. And from here, we're able to inform whether this is good for both photovoltaic or photocatalytic application. So I hope I've been able to convince you that we kind of have engineered 2D materials here for photovoltaic and photocatalytic application. Next slide, please. So here, this is part of the bread and butter research we do at HISA. So the tricky thing about this kind of calculations is that they are typically very large. So I'm looking at surfaces with about, I said 120 atoms, but typically they are larger than that. Now, the problem with this kind of big calculations is that you actually need the CHPC. So we have our cluster and we use our cluster. Part of the problem, apart from just using our cluster, is the amount of calculations. So the system has 120 atoms, and then I have to do 210 calculations typically. So I think this is pretty more because with the current stage of things, you have to restart some calculations after a while. So one calculation could take about 2 days, sometimes more. So 210 times 2 days, that's practically not possible to do. So this is so the solution we used was the CHPC. The next slide, please. So recently we published this work, I think this year. This work was published this year. So just talk about, we introduced something called surface modifiers on platinum. Now, the problem with a material like platinum is deactivation. So for a lot of you that do catalysis, when you use platinum, we worry about deactivation. I'm showing for the PT211 and 311 surfaces. We've also done for the PT111 surfaces. And this work was subject of a recent a patent we filed like last year. So this work I mean, people say you can't patent computational work, but we successfully did. So it's kind of cool. So from what we've done here, we introduced silicon, sulfur, phosphorus, and tin as surface modifiers. I choose the term surface modifiers instead of catalytic poisoners. The reason is because at very low concentration, we found out that it can modify the surface. If the concentration increases, we found out that it poisons the surface. And first of all, what we did was we wanted to find out if our surface, if these modifiers would adsorb stably on the surface, and we found out they all adsorb stably on the surface, as you can see in this table here. The next thing we wanted to evaluate was, back please, yeah. The next thing we wanted to evaluate was, the reaction and the reaction intermediates going to stably bind on the surface. We also found out that these all bind stably on the surface. So this gives us confidence to be able to do our reaction. So next slide, please. So here I just showed the full dehydrogenation pathway. I don't know if all of you are conversant with LOHC dehydrogenation, so I'll just give a short discussion about that. For you to, when you have your liquid organic hydrogen carrier, the reason why they are called liquid organic hydrogen carrier is that you can recyclably take out the hydrogen on them and use it for whatever you need your hydrogen for. So for your gas plants or whatever reaction. And then you can actually, the same molecule, you can put back your hydrogen. So you hydrogenate and you dehydrogenate. And so this is kind of a very cyclic reaction. We expect that our molecules are stable, our molecules wouldn't dissociate when you do this. So I showed the key result here, which is the overall reaction. The full details are in the paper. In the overall reaction, we found that, so we looked at PT211 and PT311. Generally, if you look at the curve I've shown, it's sort of not the trends are not very smooth. But what you would observe is that the PT211 and the PT311 compared to the pristine surface without any of these modifiers, the energies are sort of lower, up to about three surface modifiers. And also just think about it, consider that the surface we are considering is not so big. So we also intend to in the future do like a much bigger surface, but we'll evaluate that. So the key result here is that we were able to enhance the catalytic dehydrogenation behavior of our platinum at low concentration of these dopants. And part of this result has motivated other results. And this is something that has been published in other papers. So the next slide, please. So in this project, the key thing about what we're doing here is still trying to reduce the amount of platinum we have. So the first part was we modified the platinum surfaces. The second part is to reduce the platinum loading we have. So here we form different alloys of platinum. So if you look at the number of calculations, we have about 110 calculations. And so if you just motivates why we need CHPC based on our system size and the number of calculations we have to do. Next slide, please. So this paper was recently published. So the paper was published in MDPI, and part of the reason why we decided to publish here was the grant application that funded this required we publish open access. So in the first paper we published in Applied Surface Science, and we had to now publish open access, which is really expensive. So here we went to a slightly more cheaper journal. So we considered, we used the convex hull approach, and most of you are familiar with this. This is implemented in materials project to determine what alloys are stable. So you can also use different methods to determine various stable alloys. But to reduce our configurational search and the scope of the study, we used the convex hull approach. From here, we used the wove construction to look at the most dominant surfaces for this system. Unlike the previous study where we looked at PT211 and PT311 that were less dominant, in here we are like considering the most dominant surface. And part of the reason why we looked at less dominant surface in the previous case for platinum was because we've already done the dominant surface. So the next slide, please. So I won't go into full details, but I'll just focus more on the overall dehydrogenation energy. If you look at the overall dehydrogenation energy, something that is key is that this is for pristine platinum 111 surface. This is almost 90 kilojoules per mole. If you look at what we determine, for all our case, we kind of reduce the overall dehydrogenation energy, which is very important, which is kind of a key result. What the implication is that these different configuration, next slide, please. The implication is that all the configurations we consider, as you can see here, actually are better than platinum as dehydrogenation catalyst for methyl cyclohexane toluene. So this is kind of very important. It tells us that we can actually reduce the amount of platinum loading we have in our system and still get a better dehydrogenation catalyst. And something that is very noteworthy is that the SN4PT catalyst is the best catalyst for this reaction. Now, something that I'll just mention, a word of caution, we should remember that these are models. So we try to compare these our theoretical result with that were obtained by our European partners experimentally. The results are kind of not speaking to each other. So part of the reason might be because from an experimental point of view, the way they synthesize their catalyst is not the same way we kind of make model catalyst. And so we'd see how, because this is kind of a very tricky process to kind of get this kind of catalyst experimented. So we hope that they might get better results and better synthesis of their catalyst so we can properly compare what we have. Next slide, please. So this is the last project I'll be talking about. So this looks at water electrolysis in particular. So here we're considering doped iridium oxide for oxygen evolution reaction. Now, like I was saying, so the number of calculations we have is about 240 calculations. As well, the system size, we have about 120 atoms roughly. So the system is kind of big, so kind of also motivates why we need the CHPC to make this calculations tractable. So we have our own cluster in-house that we use as well, but we also need the CHPC to facilitate this work. Next slide, please. So I'll kind of not dwell too much about the details of this work, but I'll give you an overview. What we've done here was we looked at different dopant configurations. So we considered almost all of we considered from chromium we considered different transition metal, both 3D and 4D transition metal. And we also considered what is the possibility of replacing oxygen with fluorine and oxygen with sulfur. What motivated the thought about using fluorine and sulfur is that from an experimental point of view, these elements can be found when you do experiments. So I want to understand if we have vacancies of chlorine, vacancies of sulfur, if we have native defects of oxygen and of oxygen on the surface, how will this affect the reaction, the oxygen evolution reaction? And from here, we found out that all of our defect configurations that we considered are kind of stable. As you can see here, they are all stable, both in the cation rich and the anion rich configuration. So they are all stable. So we considered, so we looked at the binding energies and as well as the formation energies. The reason why we consider the binding energies is if you have two defect configuration, you need to know if it's actually going to stay or if it will prefer to just stay separately. So this is why we did that. Next slide, please. So don't mind this. This is kind of a very messy table to include in a presentation, but I decided just for information to include it. So we determine the various delta Gs and we determine the overpotential. So from the various delta Gs, which are your Gibbs free energy, you can get your overpotential. Now, generally, we found out that for some configurations of defect, for some defect complexes, the overpotential was reduced. Now, the novel thing we did in this study was to calculate something called the electrochemical step index. So we can also go to further approximations. So you want to see how the electrochemical step index and the overpotential scales. The problem with just using the overpotential to look at oxygen evolution reaction is that it's a very simplistic approach. And our oxygen evolution reactions are usually multi-electron processes. So you need to just go beyond a simplistic approach to be able to properly describe the system. Ideally, this is what we should get. We should get the straight line. This is more like what you should have ideally for an ideal catalyst. But this is what we have, so it's sort of not really ideal. And you should understand that this catalyst is not ideal. For you to get a perfect and a very good OER catalyst, your overpotential and your ESSI should scale. But the important thing is that we still got some few configurations of dopant that resulted in improved OER activity. As you can see here, so we have these dopant configurations that resulted in improved OER properties. So next slide. So I hope that in this short presentation, I've been able to show how computational modeling has helped in material design and material prediction, with particular emphasis on photovoltaic photocatalytics, liquid organic hydrogen reaction catalyst, as well as water electrolysis. So I'd like to thank Sherlock. So this is the EU project that we are working on that funded the research part on the platinum reaction. And I'd like to thank NETEX for providing some support to my Ethiopian student that did some of the initial work, and Nikki's as well as the CHPC for this forum. Thank you very much.
Any questions? You're not going to let him get off that easy. Thank you.
Oh, thank you, Kingsley, for the presentation. I just wanted to ask, with regards to experimental work that has been done by your partners and the catalyst, particularly for water splitting, is there any of the catalysts that is actually can be taken further and can be applied even to produce hydrogen from those reactions?
Okay. I'll just talk about it. Okay, for iridium oxide, we actually make iridium oxide in our lab. And so part of this study was we're supposed to kind of combine it with experimental work. So it's supposed to help them inform some new experimental dopants that they would introduce. So for right now, what we are still using in the lab at HISA is, I don't want to say what I don't really know, I think, but it's iridium oxide and reduced iridium oxide. So I don't think none of this hasn't been done yet for iridium oxide for water electrolysis. If you're talking of photocatalytic water splitting, those structures have not been made, but experimentally the MOS2/MOS2SE has actually been synthesized. So it's kind of nice that we are talking about synthesizing WSSE and WSSE2. So we do hope maybe somebody here in this conference would synthesize this. Yeah.
Any more questions? Seems they're going to let you get off easy.
I guess they understood everything I said.
You were good. Okay, thank you. Let's thank Kingsley.